Somewhere in the night sky above you, hidden behind the soft scatter of stars, there are objects so dense that the laws of reality bend around them, like cloth pulled tight at a single point. They do not shine. They do not reflect. They do not announce themselves. They are not even objects, not really, not in any sense that matches the word as you have used it for your entire life. They are places where the universe has folded itself so completely that the inside has become unreachable from the outside, and the outside has become invisible from within. They are silences carved into the fabric of space, and there are millions of them in our galaxy alone. You have seen the pictures, you have heard the word, you have probably been told somewhere along the way that a black hole is a kind of cosmic vacuum cleaner, a hungry, star-eating monster that sucks in everything around it and tears matter apart with terrifying strength. That description is not exactly wrong, but it is almost entirely beside the point, because the truth about black holes is not that they are violent. The truth is that they are simple. So simple that by some measures they are the simplest objects in the universe. A black hole the size of a galaxy can be described completely by just three numbers: its mass, its spin, and its charge. That is all. No surface features, no internal complexity, no memory of what fell in. A black hole erases everything it touches and reduces it to those three quiet numbers, and then it sits there, in the dark, like a final answer to a question no one asked. The closest known black hole to Earth is roughly 1,560 light-years away. That sounds far. It is not. On the scale of the galaxy, that is the next room over. Our own Milky Way contains an estimated 100 million stellar mass black holes drifting through the dark. Most of them have never been catalogued. Most of them never will be. They pass between the stars in silence, eating nothing, emitting nothing, perfectly invisible. Every time you have ever looked up at the night sky, there have been black holes between you and the stars you were looking at, and you have never been able to see a single one of them with your unaided eye, and you never will. And at the heart of our galaxy, holding the entire pinwheel of stars in a slow, gravitational embrace, there is one black hole so enormous that the planets of our solar system, the Sun itself, and every neighboring star out to a distance of light years could fall inside it and vanish without leaving a ripple. If you want to understand what a black hole really is, not the cartoon monster, not the science fiction set piece, but the actual, mathematical, observable structure that sits at the deepest end of physics, do me a small favor and hit that like button and subscribe. It helps the channel reach other curious minds drifting through the dark hours of the night. Now, settle in. Let your body soften. Let your shoulders drop. Let your eyes grow heavy. We are going to spend some time tonight inside the strangest objects in the known universe, and by the time we are done, the night sky above you will look slightly different than it did before. Let's begin. To understand a black hole, we have to start with something almost everyone gets wrong on the first try. A black hole is not a thing, it is a place, a region, a boundary in space beyond which the rules you are used to no longer behave the way you expect. If you were to draw a diagram of one, you would not draw an object. You would draw a sphere of nothing, an invisible bubble in the dark, and you would put a label on its outer edge. That label would read, in physicists' shorthand, the event horizon. Inside that label, on the inside of the bubble, lies a region of space from which nothing, not light, not matter, not information of any kind, can ever escape. Outside the bubble, the universe continues as normal. Stars shine, planets orbit, light travels in straight lines mostly. Inside the bubble, every direction you could possibly point, every path you could possibly take, every future you could possibly have, leads inward. Not because something is pulling you, because the geometry of space itself has tilted so steeply that outward simply no longer exists as a direction you can travel. Think about that for a moment. Inside a black hole, the word outward is not a forbidden direction. It is a direction that has been deleted. There is no outward. There is no path you could take, no rocket you could build, no speed you could reach. That would lead you back to the universe you came from. The universe has folded around you, and you are now inside a one-way membrane. Time itself, which used to be the river along which you travelled forward, has rotated inside the horizon. The future, the inevitable, unavoidable future that pulls every clock forward, now points inward, toward the centre. You do not fall into a black hole the way you fall off a cliff. You fall into a black hole the way you fall into tomorrow. That is not poetry. That is the actual mathematics of general relativity, the theory Albert Einstein published in 1915, written down in equations that have been verified to absurd precision by every experiment we have ever performed. Inside a black hole, the time direction and the space direction trade places. The center of the hole is not a location you could choose to visit. It is a moment in time that is going to happen to you, and there is no decision you can make and no action you can take that will prevent it from happening. The center of a black hole, in the literal sense of the mathematics, is in your future. We will spend a lot of time tonight unpacking that idea because it is the strangest single idea that physics has ever produced, and it is also true. We will look at how black holes form. We will look at what happens when one star eats another star and falls inward together. We will look at the largest black holes in the universe, monsters so vast that an entire solar system would not even register as a crumb on their surface. We will look at the smallest black holes, theoretical objects that may be smaller than an atomic nucleus and yet contain the mass of a mountain. We will look at what happens if you yourself were to fall into one. We will look at what happens to a black hole over time because, surprisingly, they do not last forever. They evaporate very, very, very slowly. We will look at the real black holes that astronomers have photographed, the one at the heart of the galaxy M87 and the one at the heart of our own galaxy, Sagittarius A star, which is so close to us in cosmic terms that you could point to it through the constellation Sagittarius on any clear summer night. And somewhere inside that point, 26,000 light-years away, 4 million suns worth of mass are compressed into a region the size of a few solar systems. And they are waiting there, exactly where they have been since before our planet existed, exactly where they will be long after our species is gone. But first, we need to step backward, because to understand what black holes are, you have to understand how anyone ever predicted them in the first place. You have to understand a moment more than a century ago when a young physicist on the Russian front in the middle of the First World War sat down with a piece of paper and a copy of Einstein's brand new equations and worked out a solution that even Einstein himself did not quite believe. His name was Carl Schwarzschild. He was 41 years old. He was serving as a lieutenant in the German army, calculating artillery trajectories on the Eastern Front. He had read Einstein's general theory of relativity the moment it was published, and within weeks, while living in trenches and barracks and snow, he had done what no one else had yet managed to do. He had found an exact solution to Einstein's field equations, not an approximation, not a numerical estimate, an exact closed-form solution describing what space-time looks like around a single, spherical, non-rotating mass. Einstein had been hoping that an exact solution might be possible eventually. He had no idea it would arrive within 6 weeks of his theory being published, written down by a soldier in a war zone, sent through the mail in a small package addressed to him personally. When Einstein read it, he was astonished. He presented the solution to the Prussian Academy in January 1916 on Schwarzschild's behalf. And buried inside that solution, hiding in the mathematics like a fossil in a stone, was a feature that would eventually be called the Schwarzschild radius, a distance from the center of any spherical mass at which something very strange happens to the equations, a distance at which time stretches to infinity from the outside view, a distance at which the geometry of space turns inside out, a distance from which, if you crossed it, you could never come back. Schwarzschild himself did not believe it described anything real. He thought it was a mathematical artifact, a quirk of the equations that would never actually occur in nature. He died of an autoimmune disease a few months later, in May 1916, still serving in the army. He never saw what his solution would eventually become. He never knew that sitting inside his equations was the first, faintest mathematical sketch of an object that would not be observed for another 60 years, that would not be photographed for another 100, that would change physics forever. The radius he found was very specific. For any mass, you could calculate it. For the Sun, the Schwarzschild radius is about 3 kilometers. That means if you could compress the entire mass of the Sun, every atom, every proton, every layer of nuclear furnace, down into a sphere smaller than the city of Boston, the Sun would become a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. If you could squeeze the entire Earth down to the size of a grape, the Earth would become a black hole. For you, sitting wherever you are right now, your Schwarzschild radius would be smaller than a single proton. If you could compress yourself to that scale, every atom of your body, every memory in your brain, every cell of your skin, you would become a black hole the size of a particle of subatomic dust. The mathematics applies to everything that has mass. It just happens that the densities required are so absurdly extreme that, for most ordinary objects, the Schwarzschild radius is a purely theoretical curiosity. For most objects in the universe, nothing ever compresses them to that point, and so the radius remains nothing more than a number in a notebook. But for stars, real, massive stars at the ends of their lives, the universe sometimes does exactly that. The universe sometimes compresses an enormous amount of mass into an unimaginably small space, all on its own, with no help from us, with nothing trying to stop it but the failing structure of a dying star. And when that happens, the Schwarzschild radius stops being theoretical. It becomes a place, a real, physical, measurable boundary in the cosmos, a border in the dark. That is where we need to go next. We need to look at the death of stars, because almost every black hole in the universe was once something else, a star, a glowing, fusing, light-giving sun, perhaps very similar to our own but larger. And every black hole, every silent, invisible point in the night sky, every gravitational well in the dark, began with a moment of failure. A moment when a star, after burning for millions or billions of years, could no longer hold itself up. A moment when gravity, the patient, slow, weakest of the fundamental forces, finally won. Every star is a slow war between two forces. On one side, you have gravity. Gravity is the pull of mass toward itself. Every atom of the star is being pulled inward toward the center, and there is a vast amount of mass in a star. The Sun, for example, contains roughly 1 octillion tons of matter. That is a 1 followed by 27 zeros. All of that mass is being squeezed inward by its own weight every second with crushing intensity. If nothing pushed back, the Sun would collapse to a point in a matter of hours. But something does push back. In the core of every star, at temperatures of tens of millions of degrees, the immense pressure of all that overlying mass forces hydrogen atoms so close together that they fuse. 4 hydrogen nuclei merge into a single helium nucleus. The new helium nucleus weighs slightly less than the 4 hydrogens that went in. That missing mass does not disappear. It becomes energy. A small amount of mass multiplied by the speed of light squared becomes a tremendous amount of energy, in accordance with the most famous equation ever written down. That energy flows outward from the core as light, as heat, as radiation. And the outward pressure of that radiation pushes back against the inward pull of gravity. The two forces balance. The star stops collapsing. It enters a long, stable, glowing middle age in which it converts hydrogen into helium and bathes the solar system around it in a steady, warm light. This is the state our Sun is in right now. It has been in this state for about 4.5 billion years. It will remain in this state for another 5 billion years or so. The balance is stable. The war is at a peaceful armistice. But the armistice cannot last forever. The hydrogen at the core is not infinite. It is being burned slowly, atom by atom, and eventually the supply runs out. When the hydrogen at the core is exhausted, fusion slows. The outward pressure weakens. Gravity, patient as always, begins to win. The core contracts. As it contracts, it heats up. And here is one of the strangest features of stellar physics. If the star is massive enough, the temperature inside the contracting core can rise high enough to ignite a new kind of fusion. Helium itself can begin to fuse, forming carbon and oxygen. The outward pressure surges back, and the star stabilizes again, briefly, in a hotter, more violent state. The star swells outward, becoming a red giant. Its outer layers expand to enormous size. Eventually, the helium runs out too. The core contracts again. If the star is heavy enough, carbon and oxygen begin to fuse, forming neon, magnesium, silicon. The cycle continues. Each new fuel burns faster and hotter than the last. Each new core contraction unlocks a new layer of nuclear reactions. In the very largest stars, this cycle proceeds all the way up the periodic table. The core, by the end, is layered like an onion. Hydrogen burning in the outermost shell, helium burning beneath it, carbon burning deeper still, then oxygen, then neon, then silicon, each in its own shell, each at its own crushing temperature. At the very center, a core of iron forms, and iron is the end of the road. Iron is the place where stellar fusion stops. Up until iron, fusing lighter elements into heavier ones, releases energy. Beyond iron, fusing heavier elements into still heavier ones, absorbs energy. Iron is the most tightly bound nucleus that exists. Once a star has built an iron core, the core stops producing outward pressure. The endless war between gravity and radiation enters its final hour. Gravity has been patient for billions of years. Iron has no defense against it. What happens next is the most violent event the universe knows how to produce. The iron core, no longer supported by fusion, collapses in less than a second. An object the size of the Earth shrinks down to the size of a city in less than the time it would take you to blink. The collapse is so fast, so total, that the falling matter slams into itself at nearly the speed of light. Electrons are pressed into protons, forming neutrons. A cascade of subatomic reactions sweeps through the core. A flood of ghostly particles called neutrinos is released, carrying away an immense fraction of the star's energy in a single instant. The collapsing core rebounds against itself with the force of 100 billion suns. A shockwave tears outward through the layers of the dying star. The outer layers, all of that hydrogen and helium and carbon and oxygen and silicon, are blasted away into space at thousands of kilometers per second. For a few weeks, the dying star outshines its entire galaxy. It becomes a supernova. A single supernova, seen from light years away, can be as bright as 100 billion suns combined. You may have seen supernova remnants in astronomy photographs, the Crab Nebula, the Cassiopeia A nebula, soft, glowing clouds of gas lit from within by their own internal energy, expanding outward across light years of empty space. Those are the funeral processions of dead stars. Each one is what is left of an outer envelope that was thrown off in a single catastrophic moment. Every iron atom in your blood, every gold atom in any ring you have ever worn, every uranium atom in the rocks beneath your feet was forged in one of those moments, somewhere in our galaxy, long before our sun even existed. You are quite literally made of dead stars. Your body contains the ashes of catastrophes that happened in places you cannot point to and times you cannot imagine. But the supernova is not the end of the story. The outer layers blow off into space. That is the funeral. The corpse, however, is still there. And what happens to the corpse depends on one single number, the mass of what is left behind, the mass of the core that did not get blown away. If the leftover core has a mass less than about 1.5 times the mass of the Sun, it becomes a white dwarf. A white dwarf is an Earth-sized lump of carbon and oxygen packed so tightly that a single sugar cube of its material would weigh about a ton on Earth. White dwarfs cannot fuse anything. They simply sit in the dark, glowing faintly with leftover heat, cooling slowly over hundreds of billions of years. The Sun when it dies in 5 billion years, will end its life as a white dwarf. It is not massive enough to do anything more dramatic. If the leftover core has a mass between roughly 1.5 and 3 solar masses, it becomes something stranger. A neutron star. A neutron star is what happens when gravity is strong enough to crush electrons into protons, leaving behind a sphere of pure, packed neutrons. A neutron star is about 20 kilometers across. It is the size of a small city. It contains the mass of 2 suns. A single teaspoon of neutron star material would weigh as much as Mount Everest. The surface gravity is so strong that, if you could somehow stand on it, you would be flattened to a film 1 atom thick before you registered the experience. Neutron stars spin at incredible speeds, sometimes hundreds of times per second, sweeping beams of radio waves across the cosmos. When one of those beams happens to cross the Earth, we see a pulse, a pulsar. The signal of a dead star ticking out across the dark every few milliseconds, perfectly regular for tens of millions of years. But if the leftover core has a mass more than about 3 times the mass of the Sun, nothing can stop the collapse. Not electron pressure, not neutron pressure, not any force known to physics. 3 solar masses is the line beyond which gravity simply wins. The core continues to fall in on itself, smaller and smaller, denser and denser, with no force capable of arresting the descent. It crosses through every density that any material has ever achieved. It crosses through the density of nuclear matter. It crosses through densities that should not exist. It keeps falling. It keeps shrinking. And at some point, it crosses its own Schwarzschild radius. The moment that happens, an event horizon forms. A boundary of no return wraps itself around what was once the core of a dying star. Inside that boundary, the equations of general relativity say the matter continues to fall faster and faster, smaller and smaller, until it reaches a state of infinite density at a single point. A singularity, a breakdown of all known physics. From the outside, however, you no longer see any of this. From the outside, you see only the boundary itself, a perfectly dark, perfectly spherical, perfectly silent surface in space. The star is gone. In its place, there is now a black hole. This is the most common way black holes are made, the death of a sufficiently massive star, the failure of all the forces that could have stopped it, and the formation of an event horizon around the collapsing core. It happens, on average, somewhere in our galaxy every century or so. It has been happening continuously for the 13.8 billion years since the universe began. And by careful counting and modelling, astronomers estimate that there are something like 100 million black holes of this kind drifting through the Milky Way at this moment, mostly invisible, mostly silent, mostly just wandering through interstellar space, the still cooling corpses of suns that died long before our planet formed. Not every black hole forms this way, however. There are at least 3 other major mechanisms by which black holes can come into being, and we are going to look at each of them, because each one produces a different kind of black hole and the differences matter. Some black holes form by quietly swallowing a companion star over millions of years. Some form by the slow accumulation of gas in the dense cores of young galaxies. Some, theoretically, may have formed in the very first instance after the Big Bang in pockets of matter that were too dense to do anything else. Each path leads to a black hole. Each path leads to a different kind of black hole. And together, those paths have populated the universe with a hidden population of objects so numerous that they outnumber the visible stars in many regions of the cosmos. Before we get to those other paths, however, we need to slow down and look at the object itself. We need to walk around it. We need to look at its parts. Because a black hole is not just one thing. It is a layered, structured region of space-time, with distinct features at different distances from the center, each one a little stranger than the last. And the first of those features, the outermost layer, the one that defines what a black hole even is the boundary we have already mentioned several times, the event horizon, the line in space beyond which there is no return. So let us walk up to it, carefully, in imagination only. Let us approach a black hole from a safe distance, in a spacecraft that does not exist, and study the strangest boundary in physics from just outside. Imagine you are floating in deep space, far from any star, far from any planet, in the cold quiet of an interstellar void. In front of you, perhaps 1,000,000 kilometers away, there is a black hole. It is a stellar mass black hole, roughly 10 times the mass of our Sun. Its event horizon is about 60 kilometers across. That is the size of a medium-sized city. The mass of 10 suns compressed into a region you could drive across in an afternoon if you somehow could. From this distance you cannot see the black hole itself because, of course, it does not emit light. What you can see is the way the stars behind it appear to ripple. The light from those background stars passes near the black hole on its way to your eyes, and the gravity of the black hole bends it. The starlight curves. It follows arcs around the black hole, slightly distorted, the way a glass marble distorts the view of whatever is behind it. The closer the light passes to the horizon, the more it bends. Stars whose light passes very close to the horizon get smeared into rings around the black hole, halos of distorted starlight encircling a dark center. This effect has a name in physics, gravitational lensing. It is the visual signature by which astronomers have detected black holes for decades, long before any of them were ever photographed directly. The bending of light by mass, the signature of a gravitational lens in the darkness. If you move closer, the dark central region grows. It is not exactly the event horizon you are seeing, by the way. The actual visual shadow of a black hole, the dark region you see in the famous Event Horizon Telescope photographs of M87 and Sagittarius A star, is larger than the event horizon itself. It is something called the photon sphere. The photon sphere is the radius at which light, traveling at exactly the speed it always does, can actually orbit the black hole. At the photon sphere, gravity is so strong that even a beam of light, the fastest thing in the universe, gets bent into a circular path around the black hole. A photon could, in principle, orbit a black hole forever at exactly that radius. In practice, the orbits are unstable. Any small perturbation and the photon either falls in or escapes outward. But for a moment, it could orbit. The photon sphere is, in some sense, the closest you can get to a black hole and still see something outside of you. From the photon sphere, you would see the entire universe wrapped around you in a ring of light. with the black hole's darkness above and below. Move closer still. Now you are within the photon sphere. The dark region in front of you fills your entire forward view. The universe, which used to be all around you, has been pushed behind you. Even the directions that used to be sideways have been bent forward. You are inside a region of space so warped that even the meaning of forward and backward has begun to shift. And now you reach it. The event horizon, the boundary itself, the moment of no return. If you have ever been told that something dramatic happens at the event horizon, that you would be torn apart or crushed or experience some physical shock, you have been told something false. For a sufficiently large black hole, crossing the event horizon is completely uneventful. There is no surface, there is no wall, there is no tactile sensation, no physical experiment you could perform inside your spacecraft would tell you that you had crossed it. You would notice nothing. Your clocks would tick normally. Your breath would come and go normally. Your radio would still pick up signals from the universe outside, distorted but recognizable. By every local measure, nothing has happened, but something has happened, quietly, invisibly, without any local indication. Your future has changed. Before you crossed the horizon, you had every possible future available to you. You could turn around, you could fire your engines, you could pick any direction and travel in it. After you cross the horizon, only one future remains, the center of the black hole. Every direction you can point now leads inward. Every path you can take leads to the singularity. Every clock you carry will tick down second by second toward the moment of your final compression. You cannot turn back. You cannot signal home. You cannot warn anyone. The mathematics has decided your future for you, and it has decided in favor of the center. This is what makes the event horizon the strangest boundary in physics. It is not a place where anything physical happens to you in the moment you cross it. It is a place where the possible futures available to you suddenly contract from many to one. You cross from a region of space where the future is open to a region of space where the future is sealed. And the universe gives you no warning, no signal, no indication that this transition has occurred. You float across it in silence, and only afterwards, when you try to leave and find that you cannot, do you realize that you are inside. There is another strange feature of the event horizon worth lingering on. Its size depends only on mass, not on what the mass is made of, not on how the black hole was made, not on the history of what fell in. Two black holes of the same mass have event horizons of exactly the same size, even if one of them was formed from the collapse of a normal star, and the other was formed from 1 billion tons of pure photons compressed by some impossible cosmic furnace. The event horizon does not remember what fed it. It does not care. It only knows the total mass it now contains. And from that one number it draws its boundary, perfectly spherical, perfectly silent, perfectly identical to every other event horizon of the same mass anywhere in the universe. This is the property that physicists call the no-hair theorem. The name is whimsical. It comes from a comment made by John Wheeler, the physicist who actually coined the term black hole in 1967, that black holes have no hair. by which he meant that they have no distinguishing features, no fingerprints, no texture, no identifying marks of any kind. If you melted 100 dictionaries and threw them into a black hole and then melted 100 encyclopedias and threw them into a different black hole of the same mass, the two resulting black holes would be utterly indistinguishable. There would be no test you could perform from the outside, no measurement you could take, no observation you could make. That would tell you which was which. The information about what fell in is gone, not hidden, not encrypted, gone, erased from the universe as far as anyone outside the horizon can ever tell. This will turn out to matter enormously when we get to Hawking radiation later tonight, because it will turn out that information cannot, in fact, be erased from the universe, not in any deep way. And the apparent loss of information at a black hole's horizon has been the source of one of the longest-running, most contentious, most beautiful arguments in modern physics. We will come back to it. But for now, simply hold the thought. A black hole is described by three numbers: mass, spin, and charge. Nothing else. The universe folds itself around a vast amount of information, and the only thing that escapes is three numbers. 3. That is the strange poverty of the description. A galaxy contains hundreds of billions of stars. A planet contains an entire history of geology and weather and life. A human being contains 100 trillion cells and a brain with 86 billion neurons, firing in patterns that produce the experience of being you. If any of those things fell into a black hole, the resulting black hole would be described by three numbers: the mass it gained, the angular momentum it gained, the electric charge it gained. The rest is gone. Let us return to your spacecraft, still hovering near the imaginary black hole. You have crossed the event horizon. From the outside, your friends watching you would not actually see you cross. From their point of view, your spacecraft would appear to slow down, redder and dimmer, as it approached the horizon, until you faded from view entirely, frozen. In the last moments before crossing, your image stretched into longer and longer wavelengths of light, your final radio signal redshifted into silence. Outside observers, by the strange logic of general relativity, never actually see anything cross a black hole's horizon. They see only the approach, slowing asymptotically, fading toward darkness. But you, on the inside, would have crossed the horizon in finite time. From your point of view, you would have moved forward smoothly, watched the universe behind you compress into a smaller and smaller patch of light, and continued falling inward, toward whatever lies at the center of the black hole. We will discuss that journey in detail later when we walk through what would actually happen to a human body inside a black hole. For now, just notice the strange asymmetry. From the outside, you never quite arrive. From the inside, you have already passed the point of no return. Both views are correct. Both are demanded by the mathematics. Different observers watching the same event see it differently because space-time around a black hole behaves differently for different observers. This is a recurring feature of black hole physics. The same event has different descriptions from different points of view. There is no single privileged viewpoint that gives you the true answer. There are many viewpoints, and they all agree with general relativity, and they all see different things. Physics calls this principle the relativity of simultaneity. Near a black hole, two observers who would normally agree on the order of events do not necessarily agree anymore. Time can stretch differently for different paths. Order of operations can be ambiguous. The universe near a horizon does not behave like the universe you are used to. Let us now turn inward. We have looked at the boundary. What lies beyond it? The interior of a black hole is one of the most mysterious regions in all of physics, not because we cannot describe it with the equations, but because the equations themselves break down. According to general relativity, the interior of a Schwarzschild black hole, the simplest type, leads inevitably to a single point at the center, a point with zero volume, a point containing all the mass that the black hole has ever swallowed, a point where the density of matter, the curvature of space-time, and the local gravitational field all become infinite. A singularity. The word sounds like science fiction. It is not. It is a precise term in physics. A singularity is a place in space where the laws of physics, as we know them, simply do not give consistent answers. The equations of general relativity, fed an input of infinite density and infinite curvature, give an output of meaningless infinities. The mathematics does not say what happens at a singularity. The mathematics says that what happens at a singularity cannot be described by general relativity at all. The theory breaks. It hits a wall. It tells you, in its own language, that something else has to take over here, and it does not tell you what. For most of the 20th century, physicists assumed that singularities were artifacts of overly simple models. The Schwarzschild solution, after all, assumes a perfectly spherical, non-rotating, electrically neutral mass. Real stars are not perfect spheres, real collapses are not perfectly symmetric. Real matter has all kinds of complications. Surely, the reasoning went, the singularity is an idealization that disappears when you do a more realistic calculation. Surely, in the actual collapse of a real star, the matter never quite reaches a single point. In 1965, the British mathematician Roger Penrose proved this assumption wrong. Penrose, working with techniques from a relatively new branch of mathematics called differential topology, demonstrated something stunning. He proved that, given the laws of general relativity, given certain very mild assumptions about the nature of matter and energy, the formation of a singularity inside a black hole is unavoidable. Not because of any particular symmetry or simplification, but as a general theorem. Any complete gravitational collapse of any kind with any internal structure will produce a singularity. The singularity is not an artifact. It is a feature. It is what gravity does when nothing can stop it. Penrose's singularity theorem was the moment when black holes stopped being a curiosity and started being a serious problem for physics. Because if singularities are inevitable, and if the equations break down at singularities, then there are places in the universe where the laws of physics, as we currently understand them, are not enough. There is something else going on. Some deeper theory must take over near the center. Some unification of general relativity with quantum mechanics, perhaps, that smooths out the infinities and gives a sensible description of what really happens at the deepest end of a black hole's geometry. That deeper theory does not yet exist. Physicists have been trying to construct it for decades. The pursuit has produced string theory, loop quantum gravity, causal dynamical triangulations, asymptotically safe gravity, and a dozen other proposed frameworks. None of them have yet given a complete, experimentally verified answer. The singularity at the center of a black hole remains the most concentrated piece of unsolved physics in the universe. What does this mean practically? It means that when you read or hear that the center of a black hole is a point of infinite density, you should understand what is actually being said. The mathematics of general relativity predicts a point of infinite density. The actual interior of a real black hole almost certainly does not contain a point of infinite density, because at extremely high densities, quantum effects must become important, and quantum effects can prevent the kind of unlimited compression that general relativity allows. We do not know what replaces the singularity in the correct theory. We just know that something has to. Whatever lies at the very heart of a black hole, hidden behind the curtain of the horizon, hidden behind any possible observation we could ever make, is a piece of physics we have not figured out. It is, in a real sense, the deepest secret in nature. And here is one of the most lovely properties of the way the universe is constructed. The singularity is hidden. Whatever is going on at the center of a black hole, whatever weird new physics is necessary to describe it, that physics never leaks out. The event horizon, the same boundary we discussed earlier, acts as a kind of cosmic veil. It hides whatever is inside. No light, no radiation, no signal of any kind can escape from inside the horizon to the outside universe. The unsolved physics is sealed off. The infinities are walled off. Whatever happens inside a black hole happens inside a black hole, and the rest of the universe is shielded from the consequences. Penrose himself formalized this property as a hypothesis. He called it the cosmic censorship conjecture. The idea is that the universe never produces a singularity without an event horizon to hide it. Singularities are always censored. The strangeness is always concealed. We can compute the existence of singularities, but we can never observe them. The cosmic censorship conjecture has not been proven. It might not be true. There might be naked singularities somewhere in the universe, places where the breakdown of physics is exposed for all to see. So far, no one has ever found one. Every singularity we have any theoretical reason to believe in is safely tucked behind a horizon, doing its strange, unknown things in private. The universe seems to prefer it that way. We will leave the singularity here, sealed behind its horizon. We will move outward, back to the surface of the black hole, back to its visible features, and ask a question that astronomers spent decades answering. How do we actually see a black hole, given that it does not emit light? The answer is that we do not see the black hole itself. We see what happens around it. A black hole sitting alone in empty space with nothing nearby is essentially undetectable. It distorts the starlight behind it slightly through gravitational lensing, but you would have to look very carefully, in exactly the right direction, with exactly the right equipment to notice. Most isolated stellar mass black holes in our galaxy have never been seen, precisely because they sit alone in the void, eating nothing, doing nothing, emitting nothing. They are perfectly invisible. But a black hole with neighbors is a different story. If a black hole has a companion star, or if it sits in a region of space with dust and gas around it, then matter begins to fall toward it. Not directly, not straight in. Matter falling toward a black hole almost always spirals. It has angular momentum. It is moving sideways, not just inward. As it falls, conservation of angular momentum spins it faster. The infalling matter forms a flat disk around the black hole, like a phonograph record, with the black hole sitting at the center hole. That disk is called an accretion disk, and accretion disks are loud. An accretion disk is one of the most violent environments in the universe. The matter in the disk is orbiting the black hole at enormous speeds, often a significant fraction of the speed of light in the innermost orbits. Different orbits move at different speeds. Faster moving inner orbits rub against slower moving outer orbits. Friction heats the matter. The temperature in the innermost regions of an accretion disk can reach tens of millions of degrees, hotter than the core of any star. At those temperatures, matter radiates intensely. It glows. It blazes in X-rays. It releases a continuous waterfall of high-energy photons. An accretion disk is, in some sense, the most efficient process in the universe for converting matter into pure radiation. As much as 10% of the mass energy of the infalling material can be released as light. By comparison, the nuclear fusion in the core of the Sun converts only a fraction of a percent of mass into energy. A black hole with an actively feeding accretion disk is one of the brightest objects in the cosmos, the brightest persistent objects we have ever observed in the universe are quasars, and quasars are nothing more than supermassive black holes with very active accretion disks at the centers of distant galaxies. The brightness comes not from the black hole itself, which emits nothing, but from the matter spiraling toward it, screaming its last as it falls. This is one of the more lovely paradoxes of black holes. The objects themselves emit no light. The matter falling into them emits more light than anything else in the visible universe. The darkness is not in the disk. The darkness is in the small region at the very center, where the disk ends and the horizon begins. Around that darkness, a halo of incandescent matter spins at the edge of physics, lighting up the surrounding cosmos with its dying glow. The Event Horizon Telescope photograph of M87, released in April 2019, shows exactly this. A bright, glowing orange ring of hot matter with a dark hole at the center. The bright ring is the accretion disk, viewed nearly face-on, distorted by gravitational lensing into a near-perfect circle. The dark hole at the center is the shadow of the event horizon surrounded by the photon sphere. It is the first direct image humanity has ever taken of a black hole. The dark patch at its center is a region the size of our solar system, 6.5 billion solar masses of compressed matter, 53 million light-years away. Light that left M87 in the age of the dinosaurs was just arriving at our radio dishes when the photograph was taken. The bright ring is the brightness of falling matter. The dark patch is the truth at the center. In May 2022, the same collaboration released a photograph of Sagittarius A star, the black hole at the center of our own Milky Way. Same structure, bright lensed ring of accretion, dark central shadow. This one is smaller in absolute size, only about 4 million solar masses, compared to M87's 6.5 billion. But it is much closer. 26,000 light-years away instead of 53 million. Same physics, same geometry, a bright halo around an empty center. The pattern is universal. Every black hole, large or small, with matter falling in, will look essentially the same. A spinning disk of luminous matter around a dark, perfectly defined silhouette. The same shape, the same architecture, repeated across the cosmos at every scale. Above and below the accretion disk in some black holes, you would also see two enormous jets of matter shooting outward, perpendicular to the plane of the disk, racing away from the black hole at speeds approaching the speed of light. These jets can extend for thousands or even millions of light-years, stretching out into intergalactic space in pencil-thin columns of plasma. They are one of the most extreme phenomena in the universe. A black hole, an object that famously eats everything that approaches it, somehow manages to launch some of the infalling material outward at relativistic speeds, sending it screaming back into the cosmos. The mechanism behind those jets is still not perfectly understood. The leading theory, developed by Roger Blandford and Roman Znajek in 1977, suggests that the jets are powered by the spinning of the black hole itself. As a black hole rotates, it drags space-time around with it. The magnetic field lines threading through the accretion disk become twisted by this dragging, wound up like a spring, and the resulting magnetic tension flings charged particles outward along the spin axis at enormous velocities. The energy for the jet comes not from the disk exactly, but from the rotational energy of the black hole. The black hole is, in effect, spinning down very slowly, donating some of its angular momentum to the jet, like a flywheel slowly transferring its kinetic energy to a generator. The galactic-scale jets emitted by some supermassive black holes are visible across millions of light-years. The famous jet of M87, the same black hole that was first photographed by the Event Horizon Telescope, was actually first observed in 1918, when astronomer Heber Curtis noticed a strange straight ray of light extending outward from the center of the galaxy. He had no idea what it was. He could not have known. It would take decades before anyone understood that the central engine of M87 was a supermassive black hole, and that the jet was a fountain of plasma launched by its rotation. Today, that jet is one of the most studied objects in extragalactic astronomy. It extends about 5,000 light-years outward from the core, glowing in radio, optical, and X-ray wavelengths, a slow-moving column of fire that has been pouring out of that black hole for tens of millions of years. Now we have a more complete picture of what a black hole actually looks like when it is not alone. It has an event horizon, an invisible boundary in space. It has a photon sphere just outside the horizon, where light can briefly orbit. It has an accretion disk of glowing infalling matter, brighter than entire galaxies. It may have relativistic jets shooting outward from the poles, spanning thousands of light-years. And at the very center, hidden behind all of this, sits the singularity, the place where physics gives up. There is one more layer of structure worth knowing about, however. We have been talking about black holes as though they all looked roughly the same. They do not. Black holes come in different sizes by enormous factors, and they fall into a small number of categories that are physically quite distinct. We need to look at each of those categories before we go any further, so let us pull back and survey the full population. The first and most familiar kind of black hole is the stellar mass black hole. These are the ones we have been describing for most of the night so far. They are the corpses of dead stars. They form when a massive star, somewhere between roughly 20 and 100 times the mass of the Sun, exhausts its nuclear fuel and collapses. The resulting black hole has a mass typically between 3 and 100 times the mass of the Sun. Their event horizons are tens of kilometers across. They are the smallest, most numerous, and most ordinary black holes in the universe. Stellar mass black holes are everywhere. As mentioned, our galaxy alone is estimated to contain about 100 million of them, drifting through interstellar space. Most of them are isolated, eating nothing, invisible. We detect them only when they are in binary systems with other stars, when matter from a companion star spills onto them and forms an accretion disk that glows in X-rays. The first black hole ever discovered, Cygnus X-1, was found this way. We will spend more time on Cygnus X-1 a little later. For now, just note that the stellar mass black holes are the ground floor of the population, the most common kind, the product of ordinary stellar death, the kind that wander through space mostly alone, mostly silent, mostly waiting. The next category up is the intermediate mass black hole. These are black holes with masses roughly between 100 and 100,000 times the mass of the Sun. They are, as the name suggests, intermediate between the stellar mass and the supermassive populations. For many years, intermediate mass black holes were a kind of theoretical gap. The mathematics suggested they should exist. There seemed to be no physical reason they could not. But observationally, they were exceedingly hard to find. They were too small to power the bright nuclei of galaxies, too large to form from the collapse of a single ordinary star. They were the missing middle of the black hole population. In the past 2 decades, that has changed. We now have strong evidence for intermediate mass black holes from several sources. Some appear to sit at the centers of dwarf galaxies, smaller cousins of the supermassive black holes at the centers of larger galaxies. Some appear to lurk in dense globular star clusters, formed by the gradual merging of smaller black holes within those crowded stellar environments. And gravitational wave detectors have now observed several mergers in which the resulting black hole had a mass in the intermediate range, providing direct evidence that such objects do exist and can be formed. The intermediate mass black hole is no longer a theoretical curiosity. It is a confirmed feature of the cosmos, just a rare one. The third category is the supermassive black hole. These are the monsters, the titans, the objects so absurdly large that the word black hole almost seems inadequate to describe them. Supermassive black holes have masses ranging from about 1,000,000 times the mass of the Sun to tens of billions of times the mass of the Sun. Their event horizons can be larger than the orbit of Pluto, larger than entire planetary systems. The largest known supermassive black hole, designated TON 618, has a mass of approximately 66 billion suns. Its event horizon, if it were placed where our Sun is, would extend nearly out to the orbit of distant trans-Neptunian objects. A single object, larger than our solar system, with the mass of an entire galaxy worth of stars, sitting in the center of a quasar more than 10 billion light-years away. Almost every large galaxy in the universe is now believed to host a supermassive black hole at its center. The galaxies that have been studied most carefully, certainly so. The Milky Way has one. Our nearest large neighbor, the Andromeda Galaxy, has one. M87 has one. Every spiral galaxy, every elliptical galaxy, every galactic core that has been observed in detail has a supermassive black hole sitting at its heart. The pattern is so universal that it appears to be a fundamental feature of how galaxies form. Galaxies and their central black holes seem to grow together, coupled through some long, slow feedback mechanism that we do not yet completely understand. The mass of the central black hole is correlated statistically with the mass of the surrounding galactic bulge of stars. This relationship is so tight that it cannot be an accident. The galaxies and their black holes are, in some sense, made for each other. They co-evolve. They feed each other. They limit each other. The history of the universe on the largest scales is partly the history of galaxies and supermassive black holes growing together over billions of years. How do supermassive black holes form? This is one of the open questions in modern astrophysics. The leading possibilities include the gradual merger of many smaller stellar mass black holes, the direct collapse of immense clouds of primordial gas in the early universe, and the growth of small seed black holes through the steady accumulation of surrounding matter. Probably some combination of all three. What is clear is that the supermassive black holes existed very early in cosmic history. We have observed quasars, the active accretion regions around supermassive black holes, at redshifts so high that the light we see from them left when the universe was less than 1 billion years old. The black holes powering those quasars already had masses of 1 billion suns or more. They grew incredibly fast by mechanisms that are still being worked out. By the time the universe was old enough to have galaxies in any familiar sense, those galaxies already had supermassive black holes anchoring them. The fourth category is the most speculative, but possibly the most beautiful: primordial black holes. These are hypothetical black holes that may have formed in the very first instance after the Big Bang, in regions where the density of matter and energy was so high that pockets of space-time collapsed directly into black holes without ever having been stars. The masses of primordial black holes could, in principle, range enormously. Some might be tiny, smaller than a grain of dust, with masses comparable to a small mountain. Some might be enormous, comparable to supermassive black holes. The range is theoretical because no primordial black hole has ever been observed. If primordial black holes exist, they might solve one of the great mysteries of modern cosmology: the mystery of dark matter. We know, from the rotation of galaxies, the bending of light by galaxy clusters, and the structure of the cosmic microwave background, that the universe contains about 5 times more matter than we can see. That invisible matter is called dark matter, and we do not know what it is made of. There are many candidates, various proposed exotic particles, modifications to gravity, and possibly populations of primordial black holes drifting through the galaxy, contributing some or all of the gravitational influence we attribute to dark matter. Observations have constrained the possibilities. Primordial black holes cannot account for all of the dark matter. in most mass ranges, but they might account for some, or they might account for the entirety of it in narrow remaining windows of mass. The search continues. Every few years, new measurements either rule out some range, or open another, or hint very faintly at a possible detection. The field is active. The question is not settled. There may be black holes the size of asteroids passing through your kitchen right now, dark matter incarnate, completely invisible, completely undetectable to your senses, contributing one part in some immense number to the gravitational pull you feel from the Earth beneath your feet. Probably not, but possibly. These are the four broad categories: stellar mass, intermediate mass, supermassive, primordial. Their masses span a range of more than 30 orders of magnitude, from grains of dust to galaxy-sized monsters. Their event horizons span a similar range, from smaller than an atom to larger than our solar system, and yet they all obey the same physics, the same general relativity that predicted them in the first place more than a century ago, when Karl Schwarzschild scribbled his solution on a piece of paper in a trench in the snow. There is one more dimension of black hole variation we have not yet discussed: rotation. So far, we have been talking mostly about the simplest kind of black hole, the non-rotating Schwarzschild black hole. Real black holes, however, almost always rotate. They inherit angular momentum from the matter that formed them, and that angular momentum has nowhere to go. It stays with the black hole. A rotating black hole is described by a different solution to Einstein's equations, found in 1963 by the New Zealand mathematician Roy Kerr. The Kerr solution is significantly more complicated than the Schwarzschild solution. It is also significantly more interesting. A rotating black hole has features that a non-rotating one does not. Most strikingly, it has a region called the ergosphere. The ergosphere is a layer just outside the event horizon shaped like a flattened ellipsoid in which space-time itself is dragged along by the rotation of the black hole. Inside the ergosphere, you cannot stand still. You cannot remain stationary relative to the distant stars. The rotation of the black hole drags all of nearby space around with it, like the rotation of a whirlpool dragging the surrounding water. Any object in the ergosphere is forced to rotate. It can still escape, in principle, because it has not yet crossed the event horizon. But it cannot avoid being swept along by the spin. The dragging of space-time by a rotating mass is called frame dragging. It is a real effect predicted by general relativity, and it has been measured faintly by the Gravity Probe B mission, which used gyroscopes in orbit around Earth to detect the slight frame dragging caused by the Earth's own rotation. The Earth's frame dragging is incredibly weak, but measurable. Near a rotating black hole, frame dragging is overwhelming. Space-time itself is being whipped into a spin so strong that inside the ergosphere, no force could possibly hold you still. You would orbit, whether you wanted to or not. The ergosphere has a wonderful theoretical property called the Penrose process. In 1969, the same Roger Penrose who proved the singularity theorem worked out a way that, in principle, you could extract energy from a rotating black hole. You drop an object into the ergosphere. While it is in there, it splits in two. One piece is thrown into the black hole in such a way that it carries negative energy. The other piece escapes outward, carrying more energy than the original object had. The black hole loses a small amount of mass energy, equivalent to the energy you have stolen. You have, in effect, used the rotation of the black hole as a kind of battery. The Penrose process is theoretical. It would be incredibly difficult to engineer. But it is allowed by general relativity, and it points to a deep fact about rotating black holes. They contain extractable energy. A rotating black hole is not just a place where things fall in, it is also, in principle, a power source. The Blandford-Znajek mechanism we mentioned earlier, the one that powers the jets of supermassive black holes, is essentially a magnetic version of the Penrose process. The energy in the jets is rotational energy stolen from the spinning of the black hole, channeled outward by magnetic fields threaded through the accretion disk. A jet that has been blazing for 10 million years across 5,000 light-years of intergalactic space is, in some sense, slowly spinning down a supermassive black hole at the center of a distant galaxy. The energy you see in those photographs of M87's jet is the rotational energy of a 6.5 billion solar mass object gradually being released through a process that connects general relativity, electromagnetism, and plasma physics into a single grand engine. All right, we have covered the broad anatomy. We have covered the categories. We have covered the strange property of rotation. Now, let us return to the question that probably brought many of you here in the first place. The question you have probably asked yourself late at night, looking up at the dark sky and feeling small. What would actually happen in the most literal, physical sense if you fell into a black hole? Let me describe this carefully, because the answer depends, surprisingly, on what kind of black hole you fell into. And it is one of the most beautiful, terrifying, mathematically precise journeys that physics knows how to describe. Let us start with the worst case, falling into a stellar mass black hole. A stellar mass black hole, recall, has an event horizon roughly tens of kilometers across. Its gravity, while extraordinary, is concentrated into a very small region of space. And that smallness, that compactness, is what makes the experience so violent. Because gravity, the gentle hand that holds your coffee cup in place on a table, also has a property called tidal force. Tidal force is the difference in gravity between 2 points. The same effect that, on Earth, causes ocean tides, because the moon pulls slightly more strongly on the side of the ocean facing the moon than on the side facing away. The difference in pull, the tide causing force, is small on Earth. It moves water around by a few meters. Near a stellar mass black hole, that difference is unimaginable. Imagine you are falling feet first toward a 10 solar mass black hole. As you approach, the gravity pulling on your feet, which are closer to the black hole, is stronger than the gravity pulling on your head, which is farther away. The difference in pull, the tidal stretching, is very small at first. You barely notice. But as you get closer, the difference grows quickly. The closer you get, the more your feet are pulled forward relative to your head. At some point, while you are still many kilometers above the event horizon, the tidal force exceeds the strength of the bonds holding your body together. Your body stretches, then it tears. Your feet are pulled away from your torso. Your head is pulled away from your shoulders. Your bones, your muscles, your cells are all ripped apart by the difference in gravity from one part of your body to the next. The physicist Kip Thorne gave this process a name. He called it spaghettification. The name is whimsical, but the process is exact. You become spaghetti, stretched out, thinner and thinner, longer and longer as you fall. Eventually, even your individual atoms are pulled apart. The protons and neutrons in your atomic nuclei are stretched into a long, thin stream of subatomic particles falling in single file toward the center. Whatever was you is now a thread of matter, a continuous filament of stretched particles, plunging inward at relativistic speed, with the singularity at the bottom of the well, still ahead, still in the future, still waiting. You do not, by the way, feel any of this, or rather, you feel only the very beginning. The moment your body starts to stretch, the same physical processes that would destroy you would also destroy your nerves, your brain, your consciousness. The disintegration is total and almost instantaneous. There is no extended suffering. There is no awareness of being torn apart. There is only the brief, sudden, decisive end of you as a coherent organism. And then there is just stretched matter, falling. That is the journey into a small black hole. For a supermassive black hole, however, the story is utterly different. And this is one of the most counterintuitive results in all of physics, because a supermassive black hole is so large, with such an extended event horizon, the tidal forces near the horizon are actually weaker than the tidal forces near a stellar mass black hole. The gravity field is gentler at the surface. The difference in pull between your head and your feet as you approach the event horizon of a supermassive black hole is much, much smaller. You can, in principle, cross the event horizon of a supermassive black hole without being torn apart. You can cross it without feeling anything at all. You float across in your spacecraft, in perfect health, with all your atoms intact and your consciousness fully present. And, depending on the size of the black hole, you might survive for hours or even days inside the horizon before the increasing tidal forces near the center begin to do their final work. Inside the horizon, however, you are no longer in the same kind of space you were before. The future has changed. Time itself has rotated. The center of the black hole, the singularity, is now in your future, not in any particular direction. You cannot point at it. You can only fall toward it, the way you fall toward next Tuesday. You experience time passing normally. You experience your spacecraft as still being intact. You can look outside in some sense and see the outside universe through your windows. The view will be deeply distorted by gravitational lensing, but it will still be there, compressed into a shrinking patch of light above you. You can have a final cup of coffee. You can write a final entry in your journal, knowing it will never be read. You can spend the last few hours of your life floating quietly in the strangest place a human being has ever been, watching the universe contract around you, knowing that you are now in a region of space that has no exit. For the largest supermassive black holes, the survival time inside the horizon is on the order of hours. For Ton 618, the 66 billion solar mass monster mentioned earlier, you could survive inside the horizon for nearly a full day before being destroyed at the center. A day of falling. A day of being inside something. A day of impossible silence in a region of the universe sealed off from the rest of reality by an invisible boundary you crossed without noticing. Then, at some point, the tidal forces begin to grow, slowly at first, then quickly, then catastrophically. The same spaghettification that happens immediately for a stellar mass black hole happens at the very end inside a supermassive one. You are pulled apart. Your atoms are stretched. Whatever you were is reduced to a stream of particles being squeezed toward a point. And then you reach the singularity, or what stands in its place in the correct theory of quantum gravity. And the rest is unknown. The mathematics breaks down. The story stops being a story. But let us go back to your friends, the ones watching from outside. What do they see during all of this? They do not see your final cup of coffee. They do not see you cross the horizon. They do not see you reach the center. From their point of view, your fate is very different from your own experience. As you approach the horizon, the light from your spacecraft becomes increasingly red-shifted. The photons leaving your hull, climbing out of the deepening gravitational well, lose energy. Their wavelengths stretch. The yellow light from your interior lamps shifts toward orange, then red, then infrared, then microwave, then radio, then darker and darker, until no instrument anywhere in the universe could detect them anymore. From outside, your spacecraft appears to slow down. The closer you get to the horizon, the slower you appear to fall. The clocks inside your spacecraft, ticking normally from your point of view, appear to be ticking more slowly from theirs. By the time you are very close to the horizon, your time has nearly stopped relative to theirs. From their point of view, you never quite reach the horizon. You hang there, suspended, frozen, becoming dimmer and redder with every passing second on their clocks, until you fade from view entirely. This is gravitational time dilation. It is real. It happens whenever you are in a gravitational field, although the effect is usually too small to notice. Clocks on the surface of the Earth tick slightly slower than clocks on satellites in orbit, by a few parts in a billion. The GPS system in your phone has to account for this difference, or it would give wildly wrong locations. Near a black hole's event horizon, the effect is not a few parts in a billion. It is unbounded. As you approach the horizon, time from the outside view slows asymptotically toward zero. Your clocks, the very heartbeat of your experience, appear from outside to be grinding to a halt. From your own perspective, however, nothing of the sort is happening. Your clock is ticking normally. Your watch is running at 1 second per second. Your heart is beating. Your breath is going in and out. Everything inside your spacecraft is behaving exactly the way it always has. The asymmetry is real, and it is irreducible. Different observers, in different places, watching the same events, will measure different durations, and there is no way to reconcile their measurements into a single objective truth. The universe near a black hole has multiple coexisting realities, all of them correct, all of them inconsistent. This is, again, not poetry. This is general relativity. This is the mathematics that has been verified to 14 decimal places by every test we have ever performed. The universe really does behave this way, and one of the consequences is that for an external observer, a black hole appears to have no interior. Nothing ever appears to fall in. Everything is frozen on the surface, at the horizon, infinitely thin, infinitely red-shifted, indistinguishable from the black background of space. From the outside, a black hole is a one-way membrane that swallows everything but emits nothing. The interior, the singularity, the gradual fall inward, all of those processes only happen from the inside. From the outside, the black hole simply absorbs. That is the bizarre symmetry of the experience. From inside, you fall in and reach a final destination. From outside, you never quite arrive. Both are correct. Both are predicted by the equations. Both have been confirmed by every observational test it has been possible to perform. There is also one more subtle wrinkle. The universe outside you, from the point of view of someone falling in, does something strange too. As you fall toward the black hole, you can look back upward, away from the singularity, at the universe outside. The light from the outside universe is still reaching you, but it is also being squeezed into a smaller and smaller cone above you, because the gravity is bending more and more of the universe into your forward view. The universe shrinks, visually, into a brighter, smaller, blue-shifted patch above your head. You see the universe blue-shifted because the photons falling in from outside gain energy as they descend into the well. They turn from yellow to violet to ultraviolet. The universe gets bluer, brighter, smaller. The future history of the entire universe, in some sense, becomes visible to you in the last seconds before you reach the singularity, compressed into a shrinking lens of accelerated time. You see, in your final moments, the entire eternity of the universe outside, hurrying through its events at impossible speed, until everything you ever knew condenses into a single bright point above you, and that point itself contracts to a final flash, and you are at the center. That description, by the way, is partly contested. The details of what an infalling observer would actually see have been refined many times, and different models give somewhat different answers. But the general principle is robust. A black hole from inside is not just a destination, it is also a window onto the deep future of the universe outside, compressed and brought into focus by the geometry of the descent. The longer you take to fall, the more of the outside universe passes during your fall. In the limit, you could, in principle, witness everything that happens outside the black hole, all of it, packed into the last seconds of your life. It is the strangest cinema ever proposed. You will not, of course, actually take this journey. No one ever has. No one ever will. Even if humans built spacecraft capable of reaching the nearest black hole, V616 Monocerotis, 3,000 light-years away, the journey would take eras, and the destination would not return any of the travelers. The descriptions we have are pure theory, verified only indirectly by observations of the matter around black holes, by simulations on supercomputers, and by the consistency of the mathematics. But every check we have ever been able to perform has agreed with the predictions. The mathematics is trusted. The descriptions are accurate, as far as we can tell. The journey is real, even if we will never make it. For most of the 20th century, after Schwarzschild's solution was finally taken seriously, and after Penrose and others worked out the basic geometry of black holes, physicists had a picture in which black holes were essentially permanent. They formed. They sat there. They sometimes ate things. They never gave anything back. A black hole in this old picture was a one-way valve. Matter and energy could enter. Nothing could ever leave. A black hole once formed would remain in place for the entire future of the universe, growing slightly each time something fell in, and never, ever shrinking. Then, in 1974, a 32-year-old British physicist named Stephen Hawking, working at the University of Cambridge, calculated something that no one expected. He combined general relativity, which describes gravity and the structure of space-time, with quantum mechanics, which describes the behavior of matter and energy at the smallest scales. The two theories had famously never been combined into a single, consistent framework. They could not be, in any complete way. But Hawking realized that, near the event horizon of a black hole, you could combine them just enough, just for the right kind of calculation, to predict something startling. Black holes are not, in fact, completely black. They emit a faint thermal glow. They radiate, and, given enough time, they evaporate. The calculation was unexpected even to Hawking himself. He had been trying to prove the opposite, in some sense. He had been working on the area theorem, which showed that the surface area of a black hole's horizon can only ever increase, never decrease. The area theorem was a thermodynamic-looking law, and it gave Hawking and other physicists an uncomfortable feeling. Black holes seemed to obey thermodynamic laws, but they had no temperature. They could not radiate. The mathematics seemed to want to give them entropy, a thermodynamic quantity, without giving them the corresponding temperature. Hawking set out to show that this analogy was misleading. He intended to demonstrate that despite appearances, black holes had nothing like a real temperature. They did not radiate. The thermodynamic analogy was a coincidence of mathematics, nothing more. He proved the opposite of what he set out to prove. The calculation, when he carried it through, came out the other way. Black holes do have a temperature. They do radiate. Very faintly. Very slowly. But they do. And the mechanism, when he worked it out, was so weird and so beautiful that it has been the subject of intense study and argument ever since. The mechanism is something like this. According to quantum mechanics, empty space is not actually empty. The vacuum is full of fluctuations, pairs of virtual particles, a particle and its antiparticle briefly pop into existence everywhere all the time, and then annihilate each other and vanish back into nothing. They borrow energy from the vacuum, in accordance with the uncertainty principle, and they pay it back almost instantly. They exist for so short a time that they cannot be directly observed, but their effects are very real. They contribute to the measurable energy of the vacuum. They produce the Casimir force between nearby uncharged plates. They are an essential feature of how the universe is built at the smallest scales. Now, consider what happens to these vacuum fluctuations near the event horizon of a black hole. Pairs of virtual particles are popping into existence at the horizon just as they do everywhere else. Most of them annihilate within a tiny fraction of a second and vanish, but occasionally The geometry of the black hole intervenes. One of the two particles, the one slightly closer to the horizon, falls inward and crosses the horizon. The other, the one slightly farther away, escapes outward. They can no longer annihilate because they are separated by an unbridgeable boundary. The outward travelling particle survives. From the outside, it appears to be emitted by the black hole. From its own perspective, it was a quantum fluctuation that just happened to have a partner fall into the black hole. Either way, the effect is the same. A particle leaves the vicinity of the black hole, carrying energy outward, and a corresponding decrease in the black hole's mass occurs. The black hole has, in effect, radiated. It has given up a tiny bit of its mass energy as a particle travelling outward into space. This is Hawking radiation. It is a thermal spectrum, indistinguishable from the blackbody radiation of a hot object. The temperature of the radiation depends inversely on the mass of the black hole. The smaller the black hole, the higher the temperature, the faster it radiates. The larger the black hole, the colder, the slower the radiation. How slow are we talking? For a stellar mass black hole, 10 solar masses, the Hawking temperature is about 6 millionths of a Kelvin. That is colder than the cosmic microwave background, which currently fills the universe at a temperature of about 2.7 Kelvin. As long as the cosmic microwave background remains warmer than the black hole actually absorbs more radiation from the surrounding universe than it emits. It grows slowly. It does not evaporate. Hawking radiation is happening, but it is overwhelmed by the absorption of background photons. For the universe to cool to the point where stellar mass black holes can begin to evaporate faster than they absorb, the cosmic microwave background would have to drop below their tiny Hawking temperature. That will happen eventually, as the universe continues to expand and the cosmic microwave background continues to redshift. But it will take an incredibly long time. The current temperature of the CMB is dropping at a rate set by the expansion of the universe. For the CMB to fall below 6 millionths of a Kelvin, the universe will have to expand to an enormous size, far beyond its current scale. We are talking about timescales much longer than the current age of the universe, possibly tens of billions of times longer. Once stellar mass black holes finally begin to evaporate, the process is glacial. The estimated time for a 10 solar mass black hole to fully evaporate by Hawking radiation, assuming nothing falls into it during that time, is on the order of 10 to the 67 years. That is a 1 with 67 zeros after it. To put that in perspective, the current age of the universe is about 10 to the 10 years. The evaporation time of a stellar mass black hole is 57 orders of magnitude longer than the entire history of the universe so far. The number is, in any practical sense, indistinguishable from forever. For supermassive black holes, the evaporation time is even more absurd. A black hole with the mass of M87's central object would take about 10 to the 100 years to evaporate. A 1 followed by 100 zeros. By the time supermassive black holes finish their slow decay, every star in the universe will have long since burned out. Every galaxy will have long since dissolved into dust. The universe will be a thin, cold, mostly empty void. And in that final void, the last stragglers will be the supermassive black holes slowly, slowly, slowly evaporating into faint Hawking radiation, until at last, after almost incomprehensible spans of time, even they too will fade. What happens at the very end of a black hole's evaporation? In the final fraction of a second of its life, as the black hole shrinks to a tiny remnant, its temperature soars. The Hawking temperature scales inversely with the mass. A black hole the mass of a small mountain has a temperature of millions of degrees. A black hole the mass of a grain of dust has a temperature of trillions of degrees. The radiation it emits becomes more and more energetic. In the final instant, the black hole detonates. It releases its remaining mass energy in a brilliant burst of high-energy radiation, ending its existence in a flash that, depending on the size, could be visible across enormous distances of space. No such flash has ever been observed. This is, in part, because no primordial black hole, the only black hole small enough to be in the final stages of evaporation now, has ever been confirmed to exist. If primordial black holes formed in the early universe with masses around 10 to the 11 grams, the mass of a small mountain, they would be finishing their evaporation around now, exploding into bursts of gamma rays detectable by our instruments. Astronomers have searched for such bursts. They have not found any with the right signature. The absence of detections puts constraints on how many primordial black holes can exist in that mass range. So far, the universe seems to contain few or none of them. But the search continues. The discovery of Hawking radiation completely changed the picture of black holes. They are no longer eternal. They are no longer pure one-way valves. They radiate. They cool the universe, very slightly. They eventually evaporate. They are participants in the long, slow, thermodynamic story of the cosmos, not isolated exceptions to it. And, more importantly, Hawking radiation raised a problem that has occupied theoretical physicists for half a century. The problem of information. Recall the no-hair theorem from earlier. A black hole once formed is described only by mass, spin, and charge. The information about what fell in is erased as far as anyone outside the horizon can tell. Now consider what happens when the black hole evaporates. It emits Hawking radiation. The Hawking radiation in Hawking's original calculation is perfectly thermal. It is structured only by the temperature of the black hole. It carries no information about anything that ever fell in. The black hole shrinks to nothing, emits a final burst of thermal radiation, and then is gone. Whatever fell in over its lifetime, the books, the spacecraft, the stars, the planets, the consciousnesses, all of that information is now apparently gone for good, erased, lost, never recoverable. This was a problem. Because quantum mechanics, the other half of the framework that Hawking used to derive his result, has a property called unitarity. Unitarity says that information in a strict mathematical sense cannot be destroyed. The complete state of a quantum system at one time uniquely determines its state at any other time. The universe, in its full quantum description, is reversible. Whatever happened can in principle be undone by tracing the equations backward in time. The fundamental laws preserve information. Hawking's calculation, if taken at face value, broke unitarity. It claimed that a black hole could absorb a perfectly definite quantum state, then evaporate, leaving only thermal radiation behind. The detailed information about the initial state would simply be gone. The universe would have lost something in a deep, irreversible way. This was the black hole information paradox, and for decades it tore physics in half. Some physicists, including Hawking himself for a long time, sided with the calculation. Information is indeed lost in black holes. Unitarity has to be modified at the most extreme scales. Quantum mechanics, as we currently understand it, is incomplete, and the missing piece is the principle that allows information to be erased by gravity. Other physicists, including a young string theorist named Leonard Susskind, sided with quantum mechanics. Unitarity must be preserved. Information cannot be lost. Something is wrong with Hawking's calculation, even if we cannot quite say what. Information must be encoded somehow in the radiation, in subtle correlations that Hawking's approximation missed. There has to be a way for the information to come back out. The argument went on for decades. Many proposals were floated. Some involved the complete details of how a black hole forms, breaks down, and decays, accounting for every quantum scrap of information by the time the last Hawking photon escapes. Some involved exotic structures at the horizon, like firewalls or fuzzballs that imprint the infalling information on the outgoing radiation in surprising ways. Some involved a deep principle called holography, which proposes that the entire three-dimensional content of a region of space can be encoded on a two-dimensional surface at its boundary, in a way that ensures information is never truly lost. Holography turned out to be one of the most important theoretical developments in modern physics. It was the basis of the famous ADS/CFT correspondence, which provides an exact mathematical duality between a region of space with gravity and a theory of quantum fields on its boundary. A DS/CFT showed, in a class of toy models, that black holes really do preserve information. The radiation that comes out of a black hole really does encode, in fantastically subtle correlations between successive emitted particles, the entire history of what fell in. Information is not lost. It is just spread out, scrambled, encoded in a form so complicated that no realistic measurement could ever decode it. In 2004, Hawking himself conceded the argument. At a conference in Dublin, he announced that he had changed his mind. Black holes, he agreed, do preserve information. The original calculation had been incomplete. He paid off a bet he had made years earlier with another physicist on this very question, presenting an encyclopedia in lieu of the lost information. It was a moment of great theatrical generosity. 3 decades of disagreement conceded in public by the man whose original calculation had started the entire debate. Even so, the question is not completely settled. The mathematical machinery that demonstrates information preservation works best in certain idealized models. The exact mechanism by which information escapes from a realistic black hole, the one that formed from a collapsing star in our own galaxy and is now sitting in interstellar space, is still being worked out. Recent years have seen huge progress, including beautiful work involving so-called page curves, which describe the entanglement entropy of Hawking radiation over time, and complicated theoretical objects called replica wormholes, which contribute to the calculation in ways no one had previously considered. The current consensus among most working theorists is that black holes do preserve information, that Hawking radiation does encode the contents of what fell in, and that the universe as a whole continues to obey the rules of quantum mechanics even in the most extreme places. But the consensus is qualified. The story is not yet finished. Black holes remain the central laboratory for testing the boundary between general relativity and quantum mechanics. And the black hole information paradox, in its modern refined form, is still one of the most active areas of theoretical research in physics. Let us step away from theory for a while. Let us look at the actual black holes we know about, real ones, observed ones, ones with names, locations, masses, and histories. Because for all the talk about idealized event horizons and theoretical singularities, the most stunning fact about black holes is that they are not theoretical at all. They are out there. We have found them. We have measured them. We have, in 2 cases now, photographed them. They are not equations on paper. They are real objects, in real places, in the real sky. The first black hole ever discovered, or at least the first to be widely accepted by the astronomical community as a black hole, was Cygnus X-1. It was found in 1964 when sounding rockets carrying X-ray detectors mapped the sky and discovered an extremely bright source of X-rays in the constellation Cygnus. The source was eventually traced to a binary system about 7,000 light-years away. The visible component of the binary was a blue supergiant star known as HDE 22688. The invisible component, the one emitting the X-rays, had a mass of about 15 times that of the Sun and was clearly compact. It was too massive to be a white dwarf. It was too massive to be a neutron star. It had to be something else. By the early 1970s, the consensus had formed. Cygnus X-1 is a black hole, the first one humanity ever found, sitting in a tight orbit with a supergiant companion star, slowly siphoning off the companion's outer atmosphere into an accretion disk that blazes in X-rays, bright enough to be seen across 7,000 light-years of intervening interstellar dust. The discovery of Cygnus X-1 set off a kind of revolution in astronomy. Before Cygnus, black holes were still considered by many to be a mathematical curiosity. They might exist, somewhere, in some idealized form, but they had not been seen, and might never be seen. After Cygnus, the possibility became a reality. Astronomers began looking for similar binary X-ray sources elsewhere in the galaxy, and they found many. There are now dozens of confirmed stellar mass black holes in binary systems within our own Milky Way, each one a star and its companion engaged in a slow gravitational dance, the dead heavier partner pulling matter off the lighter living one, the X-rays from the accretion disk glowing across thousands of light years. Cygnus X-1 was the first. It was not the last. There is a charming side note to the Cygnus X-1 story. 2 famous physicists, Stephen Hawking and Kip Thorne, made a bet about the system in 1974. Hawking, despite having done much of the foundational work on black holes, bet against the proposition that Cygnus X-1 was a black hole. Thorne bet for. The wager was a subscription to Penthouse magazine for Thorne if he won, and a subscription to private eye for Hawking if he won. Hawking later said that he made the bet as a kind of insurance policy. If Cygnus X-1 turned out not to be a black hole, despite all his work assuming the existence of black holes, at least he would get a magazine. By 1990, the evidence had become so overwhelming that Hawking conceded the bet. He bought Thorne a subscription. He had been wrong by his own admission, and Cygnus X-1 was a black hole. It remains one of the most well-studied black holes in the universe. It was also recently remeasured by gravitational wave techniques in 2021, and its mass was revised upward to about 21 solar masses, making it one of the heaviest known stellar mass black holes in our galaxy. There are many other stellar mass black holes in the Milky Way: V404 Cygni, GRS 1915 plus 105, GRO J1655 minus 40. The list is long. Each of them is a binary system with a compact, dark, massive component eating matter from a companion, lighting up the sky in X-rays. Each one is invisible itself, but blazes with the light of its accretion. They are the foreground population, the mundane black holes, the ones in our cosmic neighborhood, the products of nearby stellar deaths, doing what black holes do slowly and quietly in interstellar space. But the most famous black holes are not the stellar mass ones, they are the supermassive ones, the ones at the centers of galaxies, the ones we have photographed. The closest supermassive black hole to Earth is Sagittarius A star. It sits at the center of our own galaxy, 26,000 light-years from where you are sitting right now. Its mass is approximately 4.1 million times the mass of the Sun. Its event horizon is about 24 million kilometers across. That is roughly 17 times the diameter of the Sun. If you placed Sagittarius A star at the location of our Sun, it would not extend to the orbit of Mercury. Its event horizon would be a relatively compact thing by solar system standards, although obviously catastrophic for any planets that happen to be inside it. Sagittarius A star was identified as a candidate for a supermassive black hole in the 1970s, when radio astronomers detected a compact radio source at the precise center of the Milky Way's gravitational potential. For the next several decades, two competing groups of astronomers, led by Andrea Ghez at UCLA and Reinhard Genzel in Germany, performed one of the most heroic feats of observational astronomy in history. They tracked individual stars orbiting Sagittarius A star over years and decades, watching the stars swing around the central object, calculating their velocities, their orbital periods, their closest approaches. The orbits were Keplerian. They were the orbits of objects in the gravitational field of a single, compact, massive central body. From the orbits, the mass and size of that central body could be calculated to extraordinary precision. The conclusion was inescapable. There were millions of suns worth of mass packed into a region smaller than our solar system. There was no other possible explanation. It had to be a supermassive black hole. Ghez and Genzel were awarded the Nobel Prize in Physics in 2020 for this work, sharing it with Roger Penrose for his earlier theoretical contributions. One of the most beautiful results from the Ghez and Genzel observations was the orbit of a star known as S2, a young blue star that swings in close to Sagittarius A star every 16 years. In 2018, S2 passed through its closest approach to the black hole at a distance of only about 120 astronomical units, 4 times the distance between the Sun and Neptune, travelling at nearly 3% of the speed of light. At that closest approach, the gravitational redshift of S2's light was directly measured, providing one of the most rigorous tests of general relativity ever performed in the strong field regime. The measurement agreed with Einstein's predictions to within the precision of the instruments. Once again, in the strangest place anyone had ever tested it, general relativity passed the test. The mathematics that Karl Schwarzschild scribbled out in a trench in 1916 still worked more than a century later when applied to an actual black hole 26,000 light-years away. Then, in May 2022, the Event Horizon Telescope released its photograph of Sagittarius A star. Years of synthesized observations from radio telescopes around the world, processed by enormous computational efforts, produced an image of a bright orange ring with a dark central shadow. The shadow was the silhouette of the event horizon lensed by gravity, surrounded by the photon sphere and accretion disk. It was the second photograph ever taken of a black hole after the M87 image from 2019, and this one was, for the human imagination, perhaps even more striking, because this was our black hole, the one at the center of our own galaxy, the one whose light, when it reached the telescopes that captured it, had been traveling for 26,000 years from a place near the center of the same Milky Way, in which our Sun and our Earth are also embedded. That black hole has been there our entire history. The light in the image left it before the last ice age ended. It travelled through the Gulf of Stars while the pyramids were built, while the Roman Empire rose and fell, while every human being who has ever lived was being born and dying. And it arrived at our radio dishes a few years ago, carrying with it the silhouette of an object that nothing in the universe can illuminate. M87 was the first. M87 was photographed in April 2019. The black hole at the center of the galaxy, M87, 53 million light-years away in the constellation Virgo, has a mass of about 6.5 billion solar masses. Its event horizon is about 38 billion kilometers across, larger than our entire solar system. The image showed a glowing orange ring, asymmetric, brighter on one side than the other because of relativistic Doppler boosting in the rotating accretion flow, with a dark shadow at the center. It was the first time any human being had ever seen, in any direct sense, the silhouette of a black hole. The photograph, when it was released at a press conference, was carried on the front pages of newspapers around the world. It was the closest thing astronomy had ever produced to a literal picture of one of the strangest objects in physics. The Event Horizon Telescope itself is not a single telescope. It is a network of radio observatories distributed across the surface of the Earth, from Hawaii to Chile to Spain to Antarctica. By combining the signals from all of these dishes using a technique called very long baseline interferometry, the network effectively functions as a single telescope the size of the entire planet. It is the only instrument capable of resolving features as small as the event horizon of a supermassive black hole at extragalactic distances. Even with the entire Earth as a baseline, the resolution required is so extreme that the image quality is, frankly, marginal. The first images are blurry. Future generations of the EHT, possibly including telescopes in orbit or on the Moon, will refine them, sharpen them, and perhaps eventually show us black holes in true, high definition. For now, we have the first two photographs. They are real, they are images of real objects. They are not artistic impressions, and looking at them is, in some sense, the closest any human being has ever come to looking directly at the central engine of a galaxy. Beyond M87 and Sagittarius A star, the inventory of known supermassive black holes is enormous. NGC 1277 hosts a black hole of about 17 billion solar masses, even larger than M87. NGC 4889 hosts one of about 21 billion solar masses. The largest reasonably confirmed supermassive black hole, again, is TON 618 at 66 billion solar masses. Some recent measurements suggest possible candidates even larger than this, in the 100 billion solar mass range. The history of black hole mass records is one of steady upward revision. As measurements improve and more galaxies are studied, the catalogue of monsters grows. Every large galaxy in the universe seems to have one. Most have 1 million to 1 billion suns of mass at the centre. A few have 10 or 20 or 50 or 60 billion. None have ever been found to be missing entirely, and every one of them is, in the language of physics, the same kind of object: mass, spin, charge. That is the entire description. 6.5 billion solar masses in a single region of curved space-time, photographed by radio telescopes across an intervening distance of 53 million light-years. The picture is, in some sense, very simple. A bright ring around a dark centre. The geometry is universal. The mathematics is universal. The objects are universal. Across every distance, every scale, every age of the cosmos, the same kind of structure appears. It is one of the strangest and most beautiful regularities in nature. There is one more class of black hole observation, however, that did not require photographs at all, did not require radio telescopes, did not require X-ray detectors. A class of observation so completely different from anything that came before that it opened a new sense for humanity, a new way of perceiving the cosmos, the detection of gravitational waves. General relativity predicts that any acceleration of mass should produce ripples in the fabric of space-time itself. The way a stone dropped in a pond produces ripples on the water. Two stars orbiting each other produce small ripples in the surrounding space-time, travelling outward at the speed of light, distorting distances ever so slightly as they pass. For ordinary masses in ordinary orbits, those ripples are far too small to detect. The Earth orbiting the Sun produces gravitational waves with amplitudes so small that they are utterly invisible to any conceivable instrument. But for the most extreme mass distributions in the universe, two black holes spiraling toward each other and merging, the gravitational waves can become enormous, detectable, measurable, heard. In September 2015, after decades of effort and billions of dollars of investment, an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a signal. Two enormous arms of LIGO, each one 4 kilometers long, set up in remote locations in Louisiana and Washington, used precision lasers to monitor the lengths of the arms to fractions of the width of a proton. On September 14, 2015, both arms recorded a brief, simultaneous, characteristic chirp, a frequency rising rapidly from about 30 Hz to around 250 Hz over a fraction of a second. The signal matched, with extraordinary precision, the predicted waveform for the final in-spiral and merger of two black holes. Two stellar mass black holes about 29 and 36 solar masses in a binary orbit, spiraling toward each other and finally merging into a single, roughly 62 solar mass black hole. 3 solar masses of energy released as gravitational waves in a fraction of a second, more power than all the stars in the observable universe combined for that brief interval. The detection was confirmed and announced in February 2016. It was one of the most important scientific discoveries of the century. The signal had been generated, calculations showed, by a binary black hole merger about 1.3 billion light-years from Earth. The waves had been travelling toward us for that long and finally reached our instruments at a moment in human history when, for the first time, we had built detectors sensitive enough to register them. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for the work that made the detection possible. Since 2015, gravitational wave detectors have observed dozens more black hole mergers, along with a handful of mergers involving neutron stars. Each merger produces a unique chirp. The waveform encodes the masses of the two objects, their spins, the distance to the event, and the orientation of the merger relative to Earth. A single chirp, lasting a fraction of a second, can reveal the existence of a binary black hole system on the other side of the universe, including the precise masses of the components, without ever having seen the system in light. Gravitational wave detection has become a kind of cosmic stethoscope, listening to the slow heartbeats of distant binary systems for years and decades before the final merger, and then witnessing the final cataclysm as it unfolds in real time. This has produced a new kind of population study. Astronomers had previously known about stellar mass black holes through their X-ray emission in binary systems. Through gravitational waves, they have now discovered that there is also a vast hidden population of black hole binaries that emit no X-rays at all, because they are not orbiting close enough to one of them being a star whose atmosphere they can siphon. These binaries are pure black hole on black hole. Both partners are dark, both are silent in light. They only reveal themselves at the moment of merger. Some of the mergers detected by LIGO have involved black holes with masses far higher than astronomers had expected. The first merger, in 2015, produced a roughly 62 solar mass black hole. By 2019, LIGO had detected a merger producing a black hole of about 140 solar masses, the first intermediate mass black hole ever confirmed by gravitational wave detection. The information now coming in from gravitational wave observatories is gradually rewriting our understanding of the population of black holes in the universe. There are more of them than we knew. They are bigger than we expected. They merge more often than we had calculated. Every new observing run produces new surprises, and the technology is improving. LIGO has been upgraded multiple times. The European Virgo detector has joined the network. The Japanese Sgr A detector is operating. Future instruments, including the space-based LISA mission planned for the 2030s, will detect gravitational waves at lower frequencies, where supermassive black hole mergers leave their signatures and even mergers at the very edge of the observable universe become accessible. There are some truly mind-bending implications of all this. When two black holes merge, the resulting object is, by the no-hair theorem, described again by just three numbers: mass, spin, charge. The history of how it formed, the specific shapes of the original binary's orbital approach, the specifics of the violent merger itself are all erased. The merger produces a wildly perturbed black hole which then rings down, oscillating like a struck bell in a pattern called the quasi-normal mode spectrum. The bell rings, the oscillations decay, and what is left is a perfectly clean, smooth, mathematically simple Kerr black hole sitting in space, no different from any other Kerr black hole of the same mass and spin. The drama of the merger is encoded entirely in the gravitational waves that radiated outward during the in-spiral and the ring-down. The resulting object retains no memory. There is something deeply lovely about this. Two enormous, complicated objects, each one originally the product of stellar life and stellar death, with their own gravitational histories, come together in the most violent event the universe can produce, and the result is a perfectly featureless, simple, calm Kerr black hole. The chaos of the merger is radiated away as ripples in space-time. The remnant settles into geometric stillness. The universe, in its capacity to swallow complexity into simplicity, has rarely done anything more striking. Beyond mergers, there are some other exotic possibilities associated with rotating and charged black holes that are worth briefly visiting before we close. They are speculative, in the sense that we have never observed them, and we have no reason to believe they exist in any practical sense. But they are mathematically allowed. They are predictions of general relativity, and they are some of the most surprising things in all of physics. A rotating black hole in the mathematics of the Kerr solution has an interior structure that is significantly more elaborate than a non-rotating one. Instead of a single point at the center, the Kerr solution has a ring singularity, an actual ring of curvature, embedded inside the inner regions of the black hole. The geometry around this ring is bizarre. According to the mathematics, an object falling into the black hole could, in principle, pass through the center of the ring without striking it and emerge into another region of space-time entirely. That other region is not part of the original universe in any obvious sense. It is mathematically a separate sheet of space-time, joined to the original by the geometry of the rotating black hole. This led, in the 1950s and 1960s, to the idea of black holes as possible bridges to other universes or to other parts of our own universe. The structure was called an Einstein-Rosen bridge, after Einstein and Nathan Rosen, who first studied it in 1935 in the simpler context of non-rotating black holes. Later, physicist John Wheeler popularized the name wormhole. A wormhole is a bridge in space-time that connects two distant places, or two different universes, through a tube whose entrance is essentially a black hole and whose exit is something called a white hole. A white hole in this picture is the time reversal of a black hole, a region of space from which matter and energy can only emerge, never enter. Matter falls into a black hole on one side of a wormhole. It emerges from a white hole on the other side. The two are connected through a tube of geometry that lies, in some mathematical sense, outside the universe in which both ends are located. It is a beautiful picture. It has been used as the basis of countless science fiction stories. It is also, in any realistic sense, completely impossible. White holes have never been observed and almost certainly do not exist. Wormholes, if they could be constructed, would require exotic forms of matter with negative energy density, which we have no way of producing in any meaningful quantity. The interior of a real astrophysical black hole almost certainly does not contain a passage to anywhere. The full Kerr solution, with its ring, singularity, and other universes, is an idealized mathematical object. Real black holes formed from collapsing stars are not expected to have any of these exotic features. The wormhole inside the math is a feature of the equations, not a feature of the real cosmos. But the mathematics is still there. It is still a true statement about general relativity, and the equations leave the door open in some abstract sense to a kind of geometry that we might never reach, but that could in principle exist. A related idea is the so-called maximally extended Kerr spacetime, in which a rotating black hole connects to an entire infinite sequence of universes, each one accessible through a different pass through the ring singularity. Closed time-like curves appear in some regions of this geometry, meaning paths through space-time that loop back to their own past. Time travel, in a strict mathematical sense, is allowed by these solutions. Again, almost certainly not in real astrophysical black holes. The mathematics is mostly an artifact of taking an idealization too literally. But the strangeness of the mathematics, the willingness of general relativity to allow these surreal possibilities, is one of the great deep features of the theory. The universe described by Einstein's equations is much richer, much weirder, much more imaginatively flexible than the universe we actually live in. Real black holes are tame compared to what the mathematics permits. They are merely strange. The mathematics allows for the truly absurd. We have come a long way tonight. We have walked from the desk of Karl Schwarzschild on the Eastern Front in 1916, scribbling equations in a snowed-in trench, to the laser arms of LIGO in Louisiana, picking up the chirp of two black holes merging more than 1 billion light-years away. We have looked at the death of stars and the birth of black holes. We have walked up to the event horizon and looked over the edge. We have considered what would happen if you crossed it, both from your own point of view and from the point of view of an observer left behind. We have looked at the singularity, the place where physics breaks. We have looked at Hawking radiation, the faint evaporation that means even black holes are not forever. We have looked at the giants at the centers of galaxies and at the small, invisible, drifting corpses scattered through interstellar space. We have looked at gravitational waves, the new sense we have built that lets us listen to mergers across the universe. And we have looked, briefly, at the strange mathematical possibilities of wormholes and white holes and other universes, the surreal backrooms of the geometry that we will probably never enter. What is still unknown? Quite a lot. We do not know what is really at the center of a black hole. The mathematics of general relativity predicts a singularity, but the mathematics also tells us that the singularity is the place where the mathematics no longer applies. There is a deeper theory we need, a theory of quantum gravity, that will replace the singularity with something else. Some smooth core, some bounce, some new form of matter, some unfamiliar phase of space-time. We do not yet know which. Several proposals are under active investigation, but none have yet been confirmed experimentally. The deepest interior of a black hole is one of the open frontiers of physics. We do not know exactly how information escapes from an evaporating black hole. We believe it does. The consistency of quantum mechanics seems to require it. The recent theoretical work on entanglement entropy and replica wormholes has provided strong support for the picture in which information is preserved. But the precise mechanism by which the contents of an infallen book are encoded into the Hawking radiation of a real, three-dimensional, astrophysical black hole is not yet fully understood. The story is being written. It is not yet finished. We do not know how the first supermassive black holes formed so quickly in the early universe. The quasars we observe at high redshifts indicate that black holes of 1 billion solar masses or more already existed within the first billion years after the Big Bang. How they got that big so fast is one of the open questions in modern cosmology. Mergers of smaller seed black holes, direct collapse of enormous primordial gas clouds, some currently unknown process, active only in the early universe. Different theories produce different predictions, and the data is still being gathered. We do not know what dark matter is. Some part of it could, in principle, be primordial black holes. Some part of it could be exotic particles. Some part of it could be something else entirely. Observational constraints rule out many possibilities, but the question is not yet settled. If primordial black holes form some fraction of the dark matter, then there is an entire hidden population of black holes drifting through the galaxy, and through your home, and through your body, and through the empty space all around you, contributing some of the invisible gravitational pull that holds the Milky Way together. Probably they do not, but they might. The galaxy keeps its secrets, and we are still cataloguing them. We do not know whether the universe contains any naked singularities. If the cosmic censorship conjecture is correct, every singularity is hidden behind an event horizon. If it is not correct, there may be regions of the universe where the breakdown of physics is exposed for direct observation. So far, we have never found one. The universe seems to be a careful keeper of its strangest secrets, but proof has not been achieved. The conjecture remains a conjecture. We do not know whether the inside of a rotating black hole really opens onto other universes, or onto closed, time-like curves, or onto any of the other surreal geometric possibilities the mathematics allows. The mathematics says yes. The real interior of a real astrophysical black hole formed from a collapsing star is almost certainly much simpler, with the inner Cauchy horizon destabilized by infalling matter and the exotic features of the idealized Kerr solution erased by the messiness of reality. But we cannot prove this, from first principles. We can only observe from outside. We do not know whether quantum gravity, when we finally have it, will look more like a refinement of general relativity, more like a refinement of quantum mechanics, or like a completely new framework that contains both as limiting cases. We have proposals. String theory, with its 11 dimensions and its vast landscape of possible vacua, suggests a kind of unification. Loop quantum gravity, with its discrete quantized spacetime, suggests a different one. There are other approaches. None have yet produced a complete, experimentally testable theory. The unification of general relativity and quantum mechanics at the most extreme regimes is the great unfinished business of theoretical physics, and black holes are the central laboratory in which the answer is being sought. These are the open questions. They are not failures. They are the edges of what we know. Every science worth doing has them. And the questions about black holes have been some of the most generative open questions in modern physics. Every attempt to answer them has produced new mathematics, new physics, new ways of thinking about space and time and gravity and quantum mechanics. They have changed the field. They have changed several fields. They have made room for entirely new disciplines like gravitational wave astronomy that did not exist a generation ago and are now producing fresh data every month. And here is the part that, for a sleepy show like this one, may be the most important to remember. None of the open questions about black holes will affect your life tonight. None of them will change the rotation of the Earth. None of them will change the warmth of your bed or the softness of your pillow. The black holes are out there, doing what they do, on their own schedule, billions of years before our time and trillions of years after. They are not coming for us. They are not hungry. They are not aware of us. They are, on the whole, the most patient objects in the universe. They sit. They wait. They have been waiting longer than our planet has existed. They will continue to wait long after our species has finished its story. The universe is full of them, and the universe is also full of room. There is no danger in the dark. Let me say that part again, because for a topic like this one, that point matters. Black holes are not threats. They are not monsters. They are not coming for us. The nearest one, recently confirmed, is more than 1,000 light years away. None of them are heading in our direction. None of them are growing into our part of the galaxy. They are simply features of the cosmos, features that have been here for billions of years, features that will be here long after the sun has died, features that wear the same face whether we see them or not. They were here when the planet you live on was forming. They were here when life began. They were here when human beings first learned to look up. They will be here when you are asleep. They will be here in the morning. They are, in some sense, the most stable features in the entire universe. There is, finally, one image I want to leave you with. It is the image of M87, the first photograph of a black hole, a bright orange ring against the deep dark of space, a dark center at the heart of the ring. You have probably seen the image. It has been on magazine covers, in textbooks, on the screens of countless documentaries. Look at it again, if you can, in your imagination. Look at the bright ring. That is matter falling. That is hot gas, spiraling, screaming, glowing as it heats. That is what infalling matter looks like around an object 6.5 billion times the mass of our Sun, 53 million light years away from the room you are in right now. Look at the dark center. That is not nothing. That is something more silent than anything else in the visible universe. That is the silhouette of an event horizon, a boundary across which nothing crosses outward, a place where the future has rotated and the universe has folded itself around a region of curved space-time so completely that even light cannot find its way out. That is what a black hole looks like when you can finally see one. It is a darkness with structure, a silence with shape, a patient, calm, perfectly stable feature of the cosmos sitting at the center of a galaxy, doing what it has always done. And every time you look at that image, you should think of one thing. That darkness is real. It is in the sky. It is one of millions like it. It is, in some sense, the truest portrait we have ever taken of nature, a bright halo around a dark center, the universe captured in a single circular composition by an international team of astronomers using the entire Earth as a single telescope. That is what we know. Now let us drift toward the end of the night. Let us let the topic fade. Let us let the words slow down. You have followed me, perhaps, through hours of strange ideas, the collapse of stars, the geometry of the horizon, the slow evaporation of objects that we used to think would last forever, the brilliant ring around the silent center, the chirp of two black holes coming together 1 billion light years away, the merger of complexity into simplicity, the patient persistence of structures older than any planet, older than any star, older than the carbon and oxygen in your own body. Outside your window, somewhere in the night sky above your city, there is the constellation Sagittarius. If you cannot see it, that is fine. If it is the wrong season, or the wrong hemisphere, or the wrong weather, that is also fine. Just imagine it in the direction the Earth points at the heart of our galaxy. Imagine the dark patch of the Milky Way visible on a clear night. Imagine looking through that patch, through the dust and gas and ordinary stars, past several layers of foreground to a point near the gravitational center of the entire pinwheel. There, 26,000 light-years away, sits Sagittarius A star, 4 million suns of mass, a bright accretion ring around a dark central shadow, a real object in the real sky, at this real moment. There are similar objects at the centers of every large galaxy you can see in the night sky, if you have a telescope. The Andromeda Galaxy, across the Gulf, has its own supermassive black hole. So does the Sombrero Galaxy. So does every spiral and elliptical and irregular galaxy that contains enough mass to anchor one. The universe is dotted with these silent hearts, each one a fold in space-time, each one a darkness with structure, each one a region of geometry from which no light can ever climb back out. And every one of them is patient, every one of them is calm, every one of them is, for now, where it has always been. They are not coming. They are not moving toward us. They are not waiting for an opportunity to strike. They are simply features of a universe much larger than our planet, much larger than our species, much larger than any of the things that fill your daily life. The universe has room for them. It has room for us. It has room for the soft warmth of your bed and the slow rhythm of your breath and the gradual quieting of your thoughts. Black holes will keep doing what they do. They will keep eating the matter that drifts too close to them. They will keep emitting their faint, hawking radiation, slower than slow, evaporating across timescales no human mind can really grasp. They will keep ringing down after mergers, settling into perfect mathematical simplicity. They will keep sitting at the centers of galaxies, holding the cosmos together with their quiet gravity. They will keep being themselves in the dark while you sleep. If you remember anything from this long, quiet wander tonight, let it be three thoughts. First, black holes are real. Not theoretical, not fictional, not exotic mathematical fantasies. Real objects in the real sky, observable by real telescopes, with real photographs and real measurements and real properties that have been tested to 14 decimal places. Second, black holes are simple, not complicated, not chaotic, not full of hidden internal machinery. Each one is described by mass, spin, and charge. 3 numbers. That is all. The simplest objects in the universe by some measures sit at the deepest end of physics. Third, black holes are calm, not aggressive, not dangerous to us, not threatening on any meaningful time scale. The nearest one is more than 1,000 light years away. The largest one is doing what it has done for billions of years. None of them will affect you tonight. None of them will affect you tomorrow. They are, in some sense, the most peaceful features in the entire cosmos. Real, simple, calm. Let your shoulders drop a little further. Let your jaw soften. Let your hands rest. The universe has had black holes in it for almost as long as it has been a universe. It has had them in it while every star you have ever seen has been shining. It has had them in it while the earth was formed, while the first life crawled out of the seas, while the first humans painted on cave walls, while every generation of your ancestors lived and slept and woke and worked and dreamed. The universe has held us and held its black holes side by side with no contradiction for almost 14 billion years. It will continue to do so. There is no urgency. There is no danger. There is only the slow, patient turning of cosmic time, with bright stars and dark holes and warm planets and quiet sleepers, all of us together in the same long night. The black hole at the center of our galaxy is still there. It will be there in the morning. It will be there for trillions of years after the morning. And between now and the morning, you have time to rest. Time to let go of the thoughts that have been turning in your head. Time to feel the warmth of your own body and the soft weight of the air around you. Time to drift. If you have enjoyed wandering through these strange and beautiful corners of the cosmos with me, you can like, subscribe, or leave a comment. It helps other sleepy souls find their way here. But you do not have to do any of that now. You can do it later. You can do it tomorrow, or never. It does not matter. What matters tonight is that you let yourself rest. Let your eyes close, if they have not already. Let your breath slow. Let your shoulders soften. Let the day's small worries dissolve into the great patient silence of the universe. The black holes are out there. They are not coming for you. They are simply being themselves in the dark, far away, where they have always been. And you are here, in the warmth, in the quiet, in the soft heaviness of the night. Rest now. The universe has room for you. Good night.